thanks. Thanks for coming, you guys.
Thanks for the applause.
Yeah. So today we're going to talk about interactive machine learning in music composition and performance. A lot of what we're going to discuss is related to my dissertation work, which I just completed at Princeton in December. And Meg has worked with me quite a bit on some applications of this work to cello bow gesture recognition. So we're going to talk a lot about the project that we've been working on together, and also some of the software that Meg is using in tonight's concert that's based on that software. So I'll let Meg say a little bit more about herself, if there's anything you want to add.
So those of you who were here yesterday have heard me say this already, but I'm a composer and a cellist and a programmer, sort of in that order. I'm an assistant professor of music and a core faculty member of CDAC, which is the Consortium for Digital Art, Culture, and Technology. It's sort of a multi-lens view onto digital arts. So we have philosophy, cinema and cultural studies, art, music, computer science, electrical engineering, and all these people sort of get together and try to do projects based on digital stuff. I have a BA and a master's in computer music, and then I went to Cincinnati for my doctorate and did a doctorate in composition with cognates in computer music and arts administration. I'm really kind of dedicated to making computer music an accepted art form instead of sort of the ghettoized art form that it currently is. I had an opera, was my doctoral thesis, and it was premiered at the Cincinnati Arts Center and Contemporary Arts Center, and was profiled by Apple. And that article has gotten me, I think, where I am today. So very much recommend Apple publicity. And basically I use Max MSP to create these interactive environments, either with video or sound. I've done a lot of work with dance and visual artists, and I worked for Cycling 74 for a little bit back in the day.
And I'm not going to add too much to Jesse's introduction about me. I'm a computer scientist, but music is my primary area of research, and I'm also a musician. I've been the co-director of the Princeton Laptop Orchestra, working with them for several years now. I've also worked with several industrial partners, including Microsoft Research, Imagine Research, and Smule, where I've worked on musical iPhone applications. So that's me. And now I'm going to jump into the talk, but before we get to music, I'm actually going to start with the motivating question: why is Google successful? You think about why they are so dominant in search. And if you're a computer scientist, you might say, well, obviously Google has the most advanced algorithms for search and, of course, for serving ads in the whole world. And you might also add that these algorithms are running on some of the most powerful hardware in the world. And you wouldn't be wrong, but I'm going to argue that that's not really the whole story. Consider, for example, if every time you did a Google search, you had to fill out this form, which has many tabs and, incidentally, is also in German. Or, you know, maybe Google is a nice company and they open source everything and say, well, we're going to take down Google, but we're going to give you our code base. We're going to give you access to all of our algorithms, and you can write it yourself, because we're open source and you're a programmer. Luckily for us and for Google, all we have to do is use this interface. So we type in a query and we get this interface, a list of very nicely ranked search results back. Right? So we can talk about Google's success as being a combination of first providing useful algorithms that do things that we need, but then providing usable interfaces and appropriate interactions to interface between the human and the algorithm. So people can learn how to use this really quickly. They don't have to be programmers, and they definitely don't have to know about how an algorithm works or what an algorithm even is. So I'm interested broadly in my work about the question of how to take algorithms and make them more useful and usable by real people, applying them to real problems. And specifically, I work with musicians and composers, and I'm interested in the question of how to make machine learning algorithms more useful to people doing work in music and the arts. So I'm going to jump in with an overview of interactive computer music and machine learning for anybody who's not familiar with one or both of these areas. Interactive computer music is a very broad term, and I'm not going to talk about all of it, but I'm going to talk about my conception of it, and part of it where I think there are a lot of really interesting problems to address. specifically interactive computer music performance, where you have some live human performers and you have computers that are either acting as musicians or acting as tools or instruments that people are using in the performance. And in a lot of these situations, we can talk about the computer system as having a component that senses some actions that a human does, interpreting those actions, and then responding by playing its own music, driving visuals, or doing some other action that is then exposed to the audience or to the performer. So in one example of this, we might talk about gesture recognition systems for music, in which case maybe I'm going to make hand gestures in front of a camera. So in that case, the sensed action would be some information extracted from the pixels of the camera, and I might have the computer identify that with a label like, you're doing gesture 1. Then based on that identification, the computer might decide which sound to play. And then later on, I may give it a different gesture and expect the computer to accurately identify it as, say, gesture 2, and then play a different sound in response. So in this case, we can talk about the computer as having a component that's really a model of the relationship between the sensed action and the meaning of that action. And the computer uses the meaning of that action to then decide how to respond. In a slightly different kind of interactive music system, we can talk about using the computer more as an expressive musical instrument, the way that a human violinist might play a violin. When you're playing the violin, every single minute action that you do over time affects the sound, sometimes in very understandable ways and sometimes in quite complex and mysterious ways. Even for real expert musicians, this is true. And this is part of the power of acoustic instruments. There's a lot of expressive capacity. And what makes computer instruments really cool, I think, is that in the case of a violin, there's a physical acoustic coupling between the actions of the performer and the sonic response that occurs. If you do one action, you're going to get a response that can't be modified unless you may modify the instrument of the body of the instrument, for example. But in computer music, there's these sensed actions and audio responses are decoupled, and we as instrument designers or composers have the opportunity to redesign this mapping between sensed action and sound generation. And in the literature, this is often called a mapping. We can also think of this, again, as a model or interpretation of a slightly different sort. So in any case, composers and instrument designers making music, it doesn't involve just writing notes on a page. It doesn't involve just thinking about what sounds happen over time. It involves the design of this entire system, from what actions are going to be sensed, how they're going to be interpreted, and how the computer is going to respond. And I'm really interested in this component here, which is how do we build these mappings or models or interpretations? Because this is really, in some sense, the essence of the instrument or of part of the interactive composition. And at the same time, this component can be really hard to design and to build in an effective and musical way. So that's really the work that I'm interested in. And supervised learning ends up being a really useful tool for building these models, and this is why. So I can talk again about a model in a more general sense as just a function. It takes some inputs and computes some outputs. And if you're a programmer, you build models kind of like this, maybe all the time, in the form of, say, programming functions or methods. But unlike in programming, where you're designing this model explicitly through your code, in supervised learning, you're designing this model implicitly. So using a supervised learning algorithm, you provide it some training data. And this data is going to be a set of example inputs, each paired with their corresponding output. So in this gesture example, my training data would be a bunch of maybe snapshots of hand gestures, each labeled with their appropriate label. And then the algorithm would build a model that, if everything goes well in the future, I can give the model a new input, and it's going to apply an appropriate output, in this case, gesture 1. Alright, so supervised learning is useful for several reasons. Number one, these models capture very complex relationships from the data, and they often do it quite well. So in many cases, especially in gesture and audio analysis in music, it might be impossible to sit down and write this model function explicitly. So supervised learning actually makes this model building feasible. Second of all, supervised learning algorithms, at least many of them, are designed to generalize well. So in this example here, this input that I've given the model isn't exactly like any of the inputs in the training data set. But a human would look at that and likely say, well, that's gesture 1 because I still recognize it. And a good algorithm for this task would do the same thing. So this gives us a potentially more accurate way of building models that are useful in the real world, where things change all the time. And finally, this last point really isn't talked about that much in the theoretical machine learning community, but I think it's really important. And that supervised learning circumvents the need to explicitly define these mapping functions or models, making it a potentially more efficient way of doing work. And we've certainly found in our work that even in many cases where it's possible, it's feasible to build these models explicitly and to build something that works pretty well, this gives people a much faster way to do it and a way to do it without programming or thinking in a certain low-level way about the problem. So, you know, I wish I could say that I was the first person to imagine using supervised learning for music, but people have been using algorithms for these types of applications for about 20 years now. And what got me really interested in working in this space was that clearly these algorithms have a lot of potential to be used in interesting ways in music, but up to this point, I think most of the people who've been using them, well, they're PhDs in computer science or electrical engineering. They're building a lot of their own code that they then use for themselves, and they do cool things with it, but it's not much use to anybody else. It's not generalizable. And there are all sorts of questions about how to make these systems general and accessible to musicians and applicable to a whole host of other problems that maybe PhDs in computer science aren't generally interested in, that I wanted to address by making a more general purpose system. So I've outlined some criteria for this kind of tool that I was thinking about when I started this work. And first of all, like I said, interesting is something general purpose that you can hook up to any gesture analysis, audio analysis problem, drive sound, drive music, drive MaxMSP or Chuck or SuperCLED or whatever software you're interested in. Interested in a GUI-based tool because, I mean, I'm a programmer and I love programming, but there are certain scenarios in which even people who love programming probably shouldn't be starting out writing code. Rapid prototyping, for example, ends up being a lot more rapid if you have a good tool that allows you to not make syntax errors, for example. And especially using a GUI is effective in other applications like Weka, which is a non-real-time GUI-based environment for machine learning that's really popular outside music. And what it allows is people who don't know much about machine learning to really get their hands dirty, understand the workflow that's supported by the GUI, and get on their feet. And Weka is really popular. It's actually been cited, I think, 12,000 times in Google Scholar last time I checked. So, you know, this is a big deal for people. And then finally, of course, my requirement is that it's got to run in real time, because we're musicians, we want to use things in real-time performance. And if we look at these criteria and compare it to other really popular packages for machine learning, we have some problems. But I'm going to argue, I think in the rest of this talk and in the demos that we're going to do, that it's also important to think about what kind of appropriate interactions we should support between the end user, the musician or the composer, and the supervised learning algorithms. And I think this is a really interesting part of this work. And so what do I mean by appropriate interactions? Well, I mean, where does the human fit into this process? First of all, we want the human to be able to create the training data by actually creating these examples. We want the human to be able to evaluate the trained model by maybe giving it more examples and then observing how the model behaves. And very importantly, we want the human to be able to modify the training data set and repeat this process. And this isn't something that's usually talked about in this way in more conventional machine learning contexts, but it makes a lot of sense here, right? The human's building a system for himself to use or for herself to distribute to musicians that then will practice with it. So the person presumably has a pretty good understanding of the application domain, of what makes a good model, of what makes a good input, and so on. So this is really crucial. And people have been talking about this kind of workflow for the last just a few years. in the human-computer interaction research community, and they've termed it interactive machine learning. So this is the way I'm going to use this term in the talk. All right, so there are some research questions here from a computer science standpoint that I'm also interested in. Number one, which human interactions, both in terms of workflow and in terms of user interface, are possible, especially with non-machine learning expert users, which interactions are useful. What are the practical benefits and challenges of incorporating human interaction in applied machine learning? And here, what I'm really going to focus on in this talk is how can interactive machine learning be useful in real-time and creative contexts? All right, so now I'm going to do a demo of the software that I've built. I'll give you a short overview of it, and then Meg and I will show you some musical examples. The software that I've built is called the Wekinator, and it meets these 4 criteria that I laid out earlier. It's built on the Weka API, which is how it got its name, and you can download it at Google Code. It's free and mostly cross-platform. So check it out. There's some mailing lists also if you're interested in getting started with it. Now, what does the Wekinator do? First of all, if you want to use it in performance, this is the kind of thing that would be going on, right? I have human actions, right? Person's doing something with an instrument, with some sensors, with a microphone. A feature extractor extracts features describing, really, these are like low-level statistics describing those actions of the human in numeric form. Those become the inputs to one or more models, and each of these models computes some outputs that then can be used to drive sound synthesis or animation or any other sort of dynamic process. Of course, I'm also interested in these human interactions in building the models. So the Wekinator gives you an interface to create the training data and to evaluate the models by giving them new inputs and observing what the models do. And the interface is designed so that this process of modifying or creating data, training a model, running and evaluating, and then going back to the data in order to change the model, this is pretty low overhead. Certainly less overhead than you would encounter in any other software that's been built in music. So under the hood, what's really going on is that the process that I want to drive with the Wekinator publishes the number of parameters that it wants. All right, so maybe I have volume and pitch of a synthesis algorithm. I'm going to build a separate model for each of these parameters, and each of these models is going to take as inputs one or more of the available features. So I might have features that describe the X and Y position of a joystick, maybe pixels or statistics computed on the pixels of a webcam, and that's how the models are going to be set up. Finally, these parameters can be of 3 different types. They might be real numbers, in which case this is sort of an unconstrained regression type of problem. They might be discrete labels. In the gesture 1, gesture 2 example that I was just talking about, that was a discrete label problem. We call this classification. And in the classification case, where you're selecting one of some number of labels, the Wekinator can also give you as output a probability distribution. So instead of just saying class 24 is the best label, I'll get some sort of notion of how sure was it that it was class 24, and how sure was it that maybe it might have been class 21 instead. And the learning algorithms that are implemented in the Wekinator are very standard machine learning algorithms. Bunch of classifiers, and then multi-layer perceptron neural networks for regression. And finally, the software is tailored to music. I've been working with musicians for the most part in designing the software. So it's got some built-in feature extractors if people want to use it with musical audio feature extraction or a lot of standard gestural controllers. You can also plug in your own feature extractors and synthesis modules in Chuck, which is a programming language that I work on at Princeton. But you can also plug in your own feature extraction modules and other modules for sound synthesis, animation, or whatever else you want. And the key here is that these modules communicate with the Wekinator via a very simple lightweight protocol that runs over UDP, and that's called Open Sound Control. And so what this means is if you're a composer, pretty much any software that you would use to write and perform music is going to be able to receive OSC and be controlled by this. If you're a programmer, pretty much any programming language out there has an OSC library, so you can write your own modules and plug them in. We've used it for controlling the Unity game engine. We've used it for controlling some animations. It's really pretty flexible and fun. All right, so let's do a demo. I've got the Microsoft Kinect here, and the Kinect gives me a nice depth map. I'll show you what it's sensing. Ooh. Fascinating change of resolution. All right. Okay, so here's the Kinect, and you can see it's getting a very nice 3D image of me moving in front of it. And I'm extracting some really simple features from this image, such as the location of the closest point to the Kinect and some idea of average densities in different parts of the visual field in front of it. Alright, so now I'm going to open my software, the Wekinator. It's written in a combination of Java and Chuck. And the first thing I'm going to do is set it up to receive information from the Kinect and to send information to Meg's computer. So I've got it set up. It's going to receive 28 features from the Kinect, and it's going to build 9 models, all continuous, so these are all going to be 9 neural networks, and I'm going to send it to Meg's machine. Nice thing about UDP is that you can have these modules running on different hardware. And like I said, the Wekinator has a bunch of built-in feature extractors. So if I wanted to use a trackpad, I wanted to use my motion sensor built into the laptop, a USB gaming device, any of these sorts of things. Come on in. I don't have to write any code. Right? So I can just check these boxes off. In this case, I did write some of my own code, so I'm going to just load that up here. And that's 28 features. And like I said, there's going to be a neural network created for each of these parameters. I'm not going to change any of the default settings. And this is the main interface of the Wekinator here, in which I'm going to send parameter values to Meg's Ableton Live running on her machine. So if I set each of these to a random number between 0 and 1, you're going to hear some stuff. Alright, so say I like this sound, and I want this sound to happen when I'm standing right here. So I've got these parameters set. I'm going to give it some examples, just some snapshots of me standing here in front of the Kinect. And let's find another sound that we like. I like that. So I want that to happen when I'm here. Okay, I like that. I'm going to have that happen like here. So I've just given it some pretty randomly chosen sounds matched with gestures that I want to use to play those sounds. I'm going to train my neural networks, creating these models from that training data. It'll take a few seconds here, and now I'll run this model. So this one is pretty unpredictable, and there's a lot of sound in here that sounds kind of the same. That's kind of cool. I think it's a good start. So what I'm going to do is go back to the training set and try to find some different kinds of sounds to reinsert into that data. So I'm going to take this instrument, I'm going to kind of keep the framework that's there, but I'm going to make it more complex and more interesting. So let's find some more sounds.
So you guys noticed that we've never heard that particular sound before that she's creating right now. But what's going on is it's sort of interpolating between all of her gestures, so it's controlling 9 different parameters on the synthesizer, so you can create these new timbres. And we'll hook that up again after the demo if people want to play around with it themselves.
Yeah. So I'll talk more about how people have actually used this in composition in a few minutes, but I think the important thing here is that this was really fast, right? This gave me a way to create a mapping with 28 inputs, the features from the Connect, driving 9 outputs, Meg's code, in a way that gives me some degree of control over the types of sounds and the types of gestures that I want to use. And I can build it. If I like it, I can modify it, or if I hate it, I can delete the training data and start over with something completely different.
Which we did last night.
Which we did, yeah. And the model that we created last night ended up sounding completely different than this. So it's a pretty fast way to put something together, and then at some point I can say, well, I'm pretty happy with this. Now I'm going to actually figure out what it's capable of doing. I'm going to practice gestures and really learn how to play this in a musical way, in a way that's appropriate to a composition that I'm working on, and so on. So I think the power of this demo was, hey, I built something pretty complicated, and it didn't take me very long, and I still have some control over shaping it. This is definitely not the only way that people have used the Wekinator. Another thing that I might want to do with it is build something that's a little bit more simply controlled, something a little bit more understandable. If I have an idea of, well, I'd really like to control the volume of this by raising my hands up and down, and I maybe want to have me stepping back and forth change the amount of distortion. So I'll show you another example of how it's possible to do that. I'm going to use a slightly different feature extractor. This is one that we experimented with yesterday, and it ended up being pretty cool. And I'll run that.
And
Same.
the audio.
Go ahead.
The audio for this one is actually the piece that I'm playing tonight that has video. It's a fixed media piece, but because I wrote it in Ableton Live, we can start to interact with it. So this is a little preview of tonight's concert.
Yeah. And here you'll see I can do some feature selection. I can say I want parameter 1, which is volume, to be controlled just by up and down position. So I can view my features and say I want maybe the closest depth to be the only thing that controls parameter 1. So that's what we did in the file that we created yesterday. Let's see. So I'm going to... Why are you incompatible? That's because I didn't change the feature extractor. Alright. Going back to the features I was using before. Sorry about that. So in performance, often the way that people use this is to build their instrument, create their piece ahead of time, save the entire state of the Wekinator, and then just launch it. So your piece, or your instrument, is immediately ready to play as soon as you sit down to play it. That isn't always the case. One of the first pieces I did with this was actually using the training process in an expressive way, and the performers were evolving their instruments over time. So let's see if that works. There we go. So I've loaded this up, and it should be trained already, and we're just going to run it. And help if I'm extracting features. Alright. Some sound?
Yeah, it's fine.
So I've got volume with my hand height. And as I move closer and further away, I get some effects. And if we had a stereo system in here, you would hear panning as I do this. Alright, so you get the idea pretty quickly. So that's another way of using this. There's one other way of using this, which we'll show you in a couple minutes when we get out the cello and show you some cello gesture recognition. Alright, so I'll close this and back to my slides. Interesting.
It likes to change your resolution.
Yeah, so I'm on my 4th resolution so far this morning. Hopefully this will work. Not so much. Here you go. Also wrong resolution. Whoa. Okay. Okay, so almost, come on. There we go. Okay, so I, in my dissertation work, ended up using this with several types of composers and musicians for a few different kinds of projects. First of all, about a year and a half ago, I worked with some professional and grad student composers at Princeton. Oh, thanks. And we used what's called a participatory design process to experiment with the software, see how it might be really useful in composition, and then improve the software. So people would give me their suggestions on what they felt was really compelling or what needed to be changed, and I'd implement all the changes, come back, and we'd reevaluate it as a group. And people in that seminar ended up really focusing on this continuous instrument building task, like the sorts of things that I was doing with the Connect. And out of that, several people ended up composing pieces or building instruments that they then used in performance at least once. And this is a really cool instrument. This is a friend of mine, Michelle Nagai, and she was walking down the street one day in Princeton and found a piece of tree bark and said, I need to make an instrument out of this. So she picked it up, took it home, attached 50 or so light sensors in the bark of the tree, and hooked it up to an Arduino, hooked that up to the Wekinator, hooked the Wekinator up to Max MSP, software that is pretty standard among composers. And she trained a set of neural networks to control the sound of her piece when she moved her hands over the bark, or she tilted towards and away from different light sources in the room. And this was a really cool project. I unfortunately don't have any video of it, but she was one of the first composers in the seminar to create a full piece out of it. The next piece I do have a video for, and this is called Clapping Machine Music Variations. This was done by Dan Truman, who's on faculty at Princeton. And in the Princeton Laptop Orchestra, one of the things we're really interested in is how to give visually compelling and interesting performances. And so you can see several people here with their arms out, and what they're doing is using this USB controller that was actually created for a PlayStation golf game. And it has these tethers, these strings with tension that pull out, and you can use it essentially as two 3D joysticks attached to your hands. Need to pay my credit cards today. So I'm going to show you a video of this. In particular, of one of the students playing this instrument. So this instrument was created with the Wekinator to control a physical model called the blowtar. And it's the kind of high-pitched, now low-pitched sound, kind of growly. So that's just a taste of that piece. And then the third piece that I studied that was written with Wekinator was done by an undergraduate student of ours named Raymond Whitecamp, who made a piece. I'll show you a little video clip in which performers are actually using the motion sensors inside the laptops. They're tilting the laptops around, and they're also hitting the laptops. And the Wekinator's detecting where people are hitting the laptop and using that to trigger sounds. So here's Raymond's piece. So his was also a really fun piece and totally different aesthetically from Dan Truman's. All right. We also use this in teaching. A lot of the students ended up building interactive installations for the final project. Everybody else also used it in the midterms. And we had students building continuous and discrete interactive systems, learning about machine learning, and we did a lot of data collection and discussion with these students to do the serious research part of the research. The fourth study that I'm going to talk about that we're really going to go into detail on is the work that I've done with Meg. And Meg is in possession of this really cool thing called the Cabo. You want to tell us about the Cabo?
Yeah, so the Cabo was developed by Keith McMillan, who is also the inventor of the Zeta line of instruments. So he is a guitar player. He's really interested in computer music, and he's very much interested in the expressive capabilities of string instruments. So a lot of research has been devoted to keyboards. And he, as a guitar player, was like, I want there to be a way for me to get input from my guitar into a computer, and he sort of extended that to the entire range of strings. So the Cabo is something that he's been working on for about 15 years, and just now the technology has become small enough and robust enough that he's capable of sort of realizing this dream. So the Zeta cello has 4 pickups, 1 for each string, and it has a multi-port pickup, and he has something called the string port, and it does super fast pitch detection. But that's only one sort of side of the equation, and most string players will tell you that where the expressivity lies is in the bow. So the bow is completely wireless. It communicates via Bluetooth, and it has a whole bunch of sensors in it that aim to sort of get the expressive data from your bowing arm. So it has a power switch, so I now have to like charge my bow and my fingerboard. So on the bow itself is a grip sensor, and I don't know if you can see my computer at all, but you can see sort of that
Here,
this
I'll
little...
show them this thing.
Okay, great. So here goes my grip. Woohoo! Right? So that's just within the bow. The bow has a 3-axis accelerometer built into it, and then a hair sensor. So that gives you 4 axes of data. And then the cello itself has an infrared emitter under the fingerboard, and there is an antenna along the length of the bow. So if I turn that on, suddenly we should start getting other data.
Joys of Bluetooth.
Yeah. Everybody?
Do you want me to talk a little bit?
Yeah.
All right. So,
Here it is.
it works now?
Yep.
All right,
It
good.
just needed to be threatened.
Always.
So now you can see my length is changing. So it knows whether I'm at the frog or the tip. It also knows whether I'm at the bridge or the fingerboard. So those of you who are composers, Ponticello versus Soltasto, it changes the sound of the instrument. And it sort of does this angle, which we keep trying to use in a useful way, but it's not consistent where I am on the bow. So use that in combination with other data, but we were trying to do something that determined what string I was playing based on angle, and it wasn't working. So we would need to give it a lot more examples.
Yeah. Alright, so,
So right now I'm sending data to my computer via Bluetooth. My computer is sending OSC data to Rebecca's computer.
yep,
So
that's why you're seeing her features moving on my screen. Alright, so in the work that we did with this in August, we sat down and built some classifiers for 8 different kinds of bow strokes. So some of these were really simple. So classifier of, is she playing up bow or down bow or neither? Some of these were much more complex, and there have been research papers published previously about things like bow articulation classification. Is she playing staccato, spiccato, legato, marcato, ricochet? I'm forgetting something. Yeah, so that's a really non-trivial problem, and that's the first reason that we wanted to use the Wekinator for this. Is bow gesture classification is hard. You really do, I think, need machine learning to do something like accurate articulation classification. The second reason, of course, is that bow gesture classification ends up being potentially very useful. It utilizes the musical expertise that a cellist or string player already has. Meg has been practicing bow strokes for I don't know how many years now, and she can she can do them very accurately. And it's something that she does over the course of a performance anyway to exercise her expert control over the instrument. And there are a lot of compositional and pedagogical applications here. If we can determine which bow strokes Meg is playing, we can hook that up to a max patch and hook them up to controlling parameters of the sound. Or we can give a classifier to a student and say, you know, how well can this classifier classify your bow strokes now that you're just learning ricochet? And it gives some feedback. So those were our motivations in this project. And now we're going to show you how we train these classifiers and kind of demo the patch that Meg is going to be using in tonight's performance. So like Meg said, the K-bow is sending data to its software on her machine. That's sending OSC to this feature extractor that I showed you with the moving parts. The feature extractor is going to send features to the Wekinator describing things like not just where is the bow, what is the current x acceleration, but also what is the maximum acceleration seen in the previous time window? What is the change in acceleration seen over the time window? And then from those features, the Wekinator is going to classify the gestures. We're sending that back to Max. So here's the feature extractor. You can see I've got these features being extracted from the sensor data. And again, I'm going to set up Wekinator to receive these features and to control a max patch. And for this example, I'm just going to show you not that. Not that one. Bow stuff. This one. So what I've got here is going to use the probability distribution output that I told you about. And what we're going to see is an estimate of Wekinator's belief that the true class is any one of these classes. And I've just put 6 classes here so we can attach this to any sort of arbitrary classification problem. And it's also going to tell us what the top class is. And so I'm going to get rid of all but one parameter. I'm going to say it's discrete. I want the distribution, and there are maybe 6 possible values. So I'll run this. I'm only going to use her bow features. I'm not going to use any of this other stuff. And I'm going to choose a classification algorithm to use. Here, I don't know. What are we going to train this on? Frog middle tip? All right. So in that case, I'm going to maybe use a k-nearest neighbor algorithm, and I'm going to use only the features that describe whether the bow is at the frog middle or tip. And in this case, that is the length sensor, and we can include some min and max just to make this a little bit more robust. We'll see what happens. Alright, so here, let's call 0 frog. So play the frog. And I'm going to record some examples. Oop. Great. Middle will be 1. Play in the middle. And she's playing on all 4 strings to give it a variety of examples, because she's actually going to be varying the string that she's playing on in the performance. So, tip. Great. Now we'll train it and we'll see what happens. Go for it. So you can see it changing from frog to middle to tip and back as she bows. And this is actually pretty good. We've had some practice building this. We know which features work. We know which classifiers do a pretty good job on this problem most of the time. So this is... what? Oh no! So, now what? She's not playing anything, but it's saying, oh, you're at the tip. So this is something that actually happens a lot in practice. We forget, hey, there's another sort of class that makes sense to classify here. So we can go back and add data for it. So number 3 is now none of the above. So do that. None of the above. Great. And I'll retrain it and rerun it. And hey, none of the above. Am I still getting your data? Yeah. Alright, so we've successfully broken it for you. Not sure why, but in practice, what we would do is probably go back, delete those training examples that we just made that messed it up, look at some of the features. I can view the features that are coming in and try to understand which features are related to the sorts of things that Meg is doing.
So, like, for that, hair on my bow is a little wonky, but in that case, if hair were not wonky, you could say if the hair is engaged, that's when.
Yep.
That's when we're on the string.
And in practice, the other thing that I would probably look at is the accelerometers, right? Is she holding the bow in a normal bowing position? If not, then we can assume that she's not at the frog, middle, or tip. So that's an example of something that you probably don't need machine learning to build a good classifier for this, but it ends up being pretty fast, and we can always retrain it. If Meg's sensor values drift, we can always change it if something about her idea of the locations that are important to her on the bow for a particular performance change. So now what do you want to do? You want to do articulation? Up, down versus up bow.
So I've used the cable myself to program, oh, is it at the frog, the middle, or the tip? It's a fairly simple problem, but the second I started going into something not even that complicated, like up bow versus down bow, are the values increasing or are they decreasing? That should be a fairly simple problem, but it was really hard. And then I saw Rebecca give this Weaponator talk right when I was sort of struggling with that, and I was like, you, me, Halo. And even on the first day, we were getting some really excellent results. So you can imagine up bow and versus down bow is changing length over time, but we're also going to incorporate the accelerometers, because at those like sort of transition points, it's really important to be able to flip it.
Yep. So what I'm going to do here is select features that describe things like the change in the length of the bow and the sort of smoothed out X, Y, and Z accelerometers. And we're going to use a decision tree because I feel like it. I'm going to delete all that data that we just made because now we're talking about a different learning problem. I could, of course, have a set of classifiers here if we wanted to classify these things all in parallel. Alright, let's do down bow. Go for it. Go for it. And usually when we do this at home, we have a foot pedal for Meg to stop and start recording herself. Alright. Yeah. What? Yes. Yeah. So, up bow. Alright, so let's see how we do just on those two. We'll train it, run it, see what happens. Go for it. Not doing so great. So what I can do, of course, is change the classifier. That might help. Let's see. SVM worked. Let's use a support vector machine. And I'm going to go back to just using our velocity features for right now.
So different algorithms give us different results based on the same data. So it's kind of odd to sort of start getting a feeling for, oh yeah, K-nearest neighbor worked really well for this, but
yep.
SVM works not at all.
Alright, so nothing really works that well. And again, we can go back to the data set, visualize the data, see what was going on. Maybe a bow sensor stopped reporting values while we were training. This happens a lot in practice because it's technology. You want to skip to the articulation? Alright, so now let's do something that's actually kind of hard and interesting, which is which type of articulation is she playing? And for this, I'm going to use a support vector machine, but with all the features. And just to make sure we're getting data. Yeah, we're getting data. I'll delete everything. What's class 0 going to be?
Why don't we just use spiccato and marcato are very, very closely related. So that, like, I mean, we can do one. We can do tuto, spiccato, marcato.
Okay.
So we have the one that's like really obvious.
All right.
So let's do tuto.
All right, go for it. Okay. Next.
Spiccato.
Okay. And next. Okay, so we've got some training examples. Let's see if this works. Go ahead.
Tuto.
So we've got class 0 is our top class.
Yep.
So that's working for the most part. Alright, so it's working pretty well. And again, if we wanted to change this, because it is pretty much doing what we want, I would say it's making some mistakes right at the beginning of the spiccato. We would give it a lot more examples of the things that it's doing wrong.
It's also neat that, like, it's hard. You have to actually, to get a spiccato going, the point is that you're sort of bouncing anyway. So to really get it going, it's not spiccato on your first stroke anyway.
Yeah. Alright, so now I'm going to open up the max patch that Meg is actually using in the performance tonight. What's the name of the patch? It's here. Here we go, bow features. So in this patch, what we're actually receiving is kind of hard for you to see probably, but we've got a classifier of batuto, not batuto, bow position, horizontal and vertical positions, articulation, whether she's playing or not playing. This isn't hooked up to the right classifiers right now, but in practice we've got all of these classifiers running in parallel. Some of them are using the distribution so that she can make sort of post-processing actions or make more intelligent decisions based on the certainty of the classifiers. So, any questions about this before we start talking again? Yep. Alright. So I have some final discussion points. Are we pretty much good until 12, or should we end earlier? Alright, so I'll go back to talking about this project and the parts of the other projects that I think are really interesting. Feel free to interrupt me if you have questions. Let's see.
So you clearly demonstrate that different algorithm not necessarily give the same result.
Yep.
So you need to clearly see what algorithm is better performing that you propose, how you actually set the feature for training.
Sure. So how do you actually decide which algorithm to use and which features to use? That's basically what you're asking?
So
Is that
you
it?
have many different algorithms. So
Yep.
do you allow users to choose their favorite, or you have some kind of experiment suggesting?
Yeah. So that's a really interesting point. At this point in the system, or in the research, wow, that's an interesting slide choice. All users see is that drop-down box, right? You get to choose one of 4 algorithms, try it out. If you don't like it, pick a different one. So there's not a lot of guidance built into the software. I definitely think it's important to give people a choice rather than enforcing ideas that, oh, support vector machines are, provably maximizing the margin to the decision hyperplane. So we should use that always. That's not a good decision for me to make as a designer, because in practice, algorithms not only have different characteristics regarding which kinds of problems they learn well, they have different characteristics with regard to how fast they train, and that ends up being really important in this kind of system. They have different characteristics with regard to what kind of parameters they expose to the user. So k-nearest neighbor, for example, is, I think you could argue it's pretty unprincipled and unsexy compared to something like a support vector machine. But the nice thing is, it works very well, and the thing that ends up being often very nice about it is that you have a parameter of how many neighbors to use. If you guys aren't familiar with this algorithm, what that does is it gives you really control over smoothness of the decision boundaries that it creates. So in something like horizontal bow position, when we were working together, Meg felt it was really important to have the bow position classifier change smoothly from frog to middle to tip. Wasn't that important that the decision boundaries were precisely where she had them in her head, because it's not like there's a ground truth decision boundary on the bow. Having KNN gives you one parameter as a user to change that smoothness, whereas support vector machine gives you a lot of parameters, none of which have very predictable effects on certain aspects of the model that users actually care about. So there's 2 interesting problems here. One is, how does anybody, no matter how much you know about machine learning, use the parameters of these algorithms and use their characteristics to build something that's most useful to them? That's a hard problem. Second part of this is, how do you make this accessible to novice users who might not even know what these algorithms are? Often, like the students that I work with, for example, they just don't use support vector machines because they see all these parameters and say, oh my gosh, this must be really complicated. I can't possibly figure out how to use this correctly. So I think there is some room for some guidance to say, hey, it looks like, your data has these different classes distributed in this manner. Obviously, if you're using boosting on a decision stump, this is not learnable. You will not get a good model for this data using this algorithm. So I think there's room there, and it's a big HCI challenge, not just in music, but in any sort of machine learning where people are using machine learning themselves to build stuff for themselves. This is a new research area, and I'm kind of going out on a limb and saying this, but I feel like there's nothing inherently hard about a lot of machine learning, right? You can learn about this workflow, and it doesn't matter how much you know about computers, you can build a model for yourself. And I think this is really exciting in things like gaming, and things like rehabilitation, all sorts of scenarios where users want to customize things that they're going to be using. So this is a hard problem. It's also a hard problem for applied machine learning researchers who also need to understand which algorithms and which features are going to be good to use. And that's a problem. So,
I sort of compare Wekinator's machine learning to like a plugin. So you, as composers, very high-level people will program their own audio effects, but the majority of people are not that skilled, not that interested, and there have been a whole bunch of programmers who have written these plugins that have dials and switches, and you can listen to the result immediately and be like, I like that, I don't like that. Exactly how Rebecca was doing the synthesis, sort of randomizing, say, do I like the way these 9 parameters are interacting? And with Wekinator, it's the same sort of thing where you're like, let me try this algorithm, let me try this different window size, let me try these different features, do I need history involved? And because it's fast, you don't actually have to sort of think and be like, oh my gosh, would k-nearest neighbor work better than SVM? You can just say, try it out. Which one do I like better? Move on. And it's lovely too because you can run, like the Batuto thing, you can use the k-nearest neighbor on that decision while running, you know, SVM on the articulations all at the same time. So you don't have to sort of get only one algorithm for your system.
I think that's important, you know, the point. I'm confused between these two. One is, actually machine learning is kind of inference, okay?
Say
based
what?
on your machine learning algorithms, actually scientific inference.
Yeah.
Okay, based on your data set, you want to try predict some kind of inference, right? But
Sometimes.
well, I think the main goal, one of the main goal, the main feature, the main motivation. But the art is creative work. You need, and you like outlier. But machine learning, we hate outliers. Right? So it's very difficult, you know, the two different worlds, but you are combined.
I agree. So, one of the next things I wanted to talk about was about the variety of different problems that people have been using the software to do. And there are very different considerations in these types of problems. In instrument building, right, we maybe don't care about accuracy at all. Maybe we're not trying to generalize. Maybe we're not trying to build a model of some existing phenomenon. Maybe complexity of the model and surprising, inspiring behaviors of the model are really good. When we're building models of K-bow gesture, we want them to be really accurate, we don't want them to be unnecessarily complex, and we really don't want to be surprised by what it does when we're in a performance. So, absolutely, I agree with you. The degree of human adaptability, I think, is also really, really key to the difference in these problems and the difference across applications. So, in the Connect example, I was able to build my model and experiment with it and say, well, maybe I really wanted to do this in a performance, but that doesn't make compelling sounds. But if I do this, that makes sounds that I really like, and that's actually a gesture that's totally acceptable to me as a performer. So I'm able to change my behavior to adapt to what the model has learned. In bow gesture recognition, we can't change what is a spiccato and what is marcato just because that makes the learning algorithm's job easier.
But
right?
we can have sloppy examples of spiccato, and then I have to... we actually experienced this where when I was training it, I was being very proper, and then we were running it, and I was like, it's wrong. Why is it wrong? And then I'm like, oh, my elbow is down low, and I'm actually not really bouncing as well as I was when I was giving it the example. So it,
as a performer, you do that all the time too. You switch between instruments. You adapt your performance to that instrument.
Yeah, and so there's always some adaptability, and I think this is again one of I have another slide on this. This is one of the things that I think makes interaction useful, not just in creative applications like instrument building, but in these more conventional applications like bow gesture recognition. There's always gray areas. One of the other places in building these algorithms that human interaction and adaptability ends up being important is something like the number of classes that you use. So in our work earlier, we were building a bow speed classifier, and Meg decided she was going to train it with 3 classes. And we gave it just a few examples, and it worked perfectly. We said, okay, well, that's great. We should make it harder for the algorithm so that we can have a more fine-grained classifier that's going to give us more useful data. So we changed the learning problem without really changing the ground truth of what bow gesture means. Similarly, if you train, we were training the up bow, down bow classifier, and it ends up being pretty hard to get a very, very robust up bow, down bow classifier if you don't treat the ends of the bow as special cases. So we actually ended up adding classes for the time in which Meg was changing from an up bow to a down bow, and having that classified as something separately, so that wouldn't give us a lot of noise in our training data.
yeah, it was odd because if I changed bow in the middle, it was still pretty accurate, but the tips were a problem, and we didn't know why.
do you find that the more feature extractors you use to define a classification, is that inherent? I mean, generally speaking, do you get more accurate results, or is there no direct correlation between the number of features that you're tracking to the classification that you're looking at?
So that's first of all, I would say there is definitely a correlation, but not in that way. I mean, there's a principle called the curse of dimensionality, where if you just add more features, even if they're all relevant, you need theoretically more data to build a classifier that's accurate for that problem, because you've increased the dimensionality of the space you're trying to find patterns in. At the same time, different classifiers behave very, very differently. If you have different features that are redundant with each other, that have noise in them, and changing the classifier is really going to have often a much bigger impact than just adding features. And of course, the most important thing is, are the features that you have relevant? If they are, you're good. If they're not, then it doesn't matter what you do. So
yeah, when we first started working, I was like, why aren't you using all my data? Use it all. And she actually did an example where she's like, all right, let's do your frog middle tip. I'm using all the data. And it was terrible, because it was looking at other data. So you have to tell it, this is what I think is important, and then it becomes much more stable.
Yeah. I'm sorry, I can't hear you.
Tolerance.
What about tolerance?
I mean, because you are interacting with real data.
Yeah.
So, I mean, for every feature you do, is there something like plus or minus? So you could use lower bound.
I use that once I program. So I'm like, if it's sort of going like this between two things and I'm using one of them as a trigger, I'm like, don't pay any attention to it, don't re-trigger a lot. So I don't know whether you have any.
No, I'm not doing any sort of explicit assumptions about noise inherent in features. Certainly you could use other kinds of algorithms where you assume that in your model there's some noise with some sort of probability distribution, and you can take advantage of that, but we really
You do the window size though, which
so that's somewhat built into the features, where I'm looking at analysis windows of the last 100 sensor values and then averaging them, that sort of thing.
It also seems like the feature extraction is separate from this, so that's probably where any data preparation.
Yeah.
So you don't need a tolerance assumption. Your train and parameter obtained, it will give you hint whether your feature set is redundant and some kind of so the analysis gives you hint whether your data set is just okay.
All right, so I'm going to wrap up. Got a few more minutes. I'm just going to hit, I think, the interesting discussion points that people haven't already raised. I can find my... There. So we talked about that. Should also mention that the models that we created ended up working really well. This was the first time that anybody's used this interactive approach to building these kinds of models. There's been a few papers in the literature where it's a more conventional approach to machine learning, where you take, a cellist or a violinist, sit them down, extract the data, and then go analyze the data, build your models offline without any sort of interaction. So all the classifiers that we built were rated by Meg as 9 or 10 out of a 10-point subjective quality scale. And if you look at the cross-validation accuracy, the numbers are also really high. And in particular, our articulation classifier for this hardest task was 98.8% accurate.
But somehow I didn't give it a 10.
But again, what's really interesting about this, which is really worth discussing, is that we logged, for every single model that Meg created, we logged the cross-validation accuracy score along with her subjective rating. So not just the final models, but every model we created. And we found that for certain classification tasks, there was no correlation between these two, or there was a negative correlation between these two. Because, well, for one thing, Meg cares about more than accuracy as defined on the training set, right? That's what cross-validation accuracy means. She cares about things like when does it change from one label to another? In particular, where, when it does make errors, are they errors of the sort that a human cellist might make, people might disagree on, or are they just egregious, I'm doing legato and it's saying I'm doing batuto? So there are a lot of different subjective qualities that are important, not just to Meg, but to anybody who's building models with the software that just aren't captured with the cross-validation accuracy score, or any sort of objective accuracy metric that you could come up with. So.
And I got very mad at it at one point because it was consistently wrong, but the way that it was wrong, like I could tell that it was like the relationship of the parameters when they were in a certain position, it actually meant something else, and I'm like, why don't you know that?
Yeah, so looking at these probability distributions gives people information that, you know, may be relevant, or it may actually just be frustrating if it suggests that a model is uncertain. So
that's why I got the 9 for articulation, because there was something, yeah, it was like Mercado was like, if it thinks it's 40% spiccato and 60% ricochet, then it's actually Mercado, and I was just like, if I can see that out of your data machine, why, yeah.
Yeah.
Machines are dumb.
They are. All right, so the other people that have used this software have also found it really useful to them. In particular, the Plork students were able to build these interactive systems really quickly, looking at 16 or 27 minutes for building different kinds of systems. This is impossible to do with programming. I mean, I'm a good programmer. I'm a really good programmer. I can't make a compelling interactive musical system in that amount of time. Like, it just, without using this sort of example-based approach. And people really enjoyed it. My comments from the homework assignment were things like, it's so cool, the Wekinator rocks. I've really been focusing, of course, on using this with professional composers and grad student composers. And these people that created these pieces that have been performed highly agreed that it allowed them to make these mappings more easily, to make mappings that were more expressive, to create a kind of music that isn't possible or is hard to create using other techniques, and to approach the process of composition in a new way. In particular, people really felt that being able to design their instruments by thinking about gesture and thinking about sound and thinking about how the two of them interact allowed them to be more effective and more expressive composers than sitting down and thinking as a programmer, whether they were explicitly programming or not, thinking about what are the kinds of sensor values I'm getting in, what are the kinds of synthesis parameters that are going to create the sounds that I want, how do I write a function that matches these two things together. So this was, I think, really key to the composers that I've been working with.
So the bow, it has 8 sensors in it, and they're sending each of those 8 values every 20 milliseconds. So if you can imagine trying to sift through that much data yourself, that's why the Wekinator rocks.
The second thing I wanted to talk about, we've already been discussing, this is the fact that human interaction is useful. And this is true not in just the expressive instrument building, not just in this more conventional bow gesture classification, but for everybody that's done this, right? The training data is an interface. It's a user interface for things like fixing mistakes. So if you have access to interact with this interface, you're able to, say, provide examples and retrain your model when it's done something you don't like. This hands-on evaluation gives people the ability to actually say, is this model doing what I want? Not just, does it have a good cross-validation or test accuracy, but is it doing what I want, and if not, what might I do to change it? I've already talked about the fact that users interacting with these models can think about, discover, and manage trade-offs between what do I want this model to express, how many classes do I want it to learn, for example, and practically speaking, how accurate can I build that kind of model with the time that I have, with the features that I have. And really interestingly, this process of providing this data, evaluating the model, and seeing what happens, led users to learn to provide better training data. And this wasn't something that we talked about in the undergraduate class, for example. People didn't really know much about machine learning, but just through experimentation, they learned things like, hey, I should minimize noise in my examples. I should provide examples that, you know, if I'm going to provide 100 examples of class A, I better provide about the same number for class B and C. people learned whether their behaviors were consistent. So Meg, for example, was having a really hard time creating a classifier that discriminated between spiccato and ricochet. It was always confusing them. So we tried different classifiers, we tried different features, didn't work. Finally, she realized, wow, my spiccato is actually too much like my ricochet. I need to change where my elbow is. She improved her technique, and then instantly we were able to build a classifier that actually worked. So this is really useful information.
But does it make your spiccato better?
Yeah.
Yeah.
Okay. Makes sense.
Yeah. I mean, I was being lazy. It's hard to do spiccato. You have to get it going, and I was just like, it's pretty much there. But what I was really like, it's very different. The ricochet is bouncing and going in one direction, and the spiccato is bouncing but switching the direction, and yeah.
Yeah. So the last thing I want to point out is that I'm really interested in this area because supervised learning ended up functioning really well as a tool for supporting creativity, and not just creativity, but embodied approaches to design. And I already mentioned this, but this is really important and interesting. I think there are a lot of implications outside of music. And looking at things that the composers have said about the Wackenerd, it's clear that this is really, really important. So somebody wrote, there's simply no way I would be able to manually create the mappings that the Wackenerd comes up with. Being able to playfully explore a space that I've roughly mapped out, but that the Wackenerd has provided the detail for, is inspiring. Another person wrote, the ability to map sound and gesture in a very immediate and intuitive yet unpredictable way is really inspiring and useful. And she liked being able to quickly map out these sorts of gestures to existing sound sets with only minor programming changes. And looking at these and other feedback that we've gotten from composers, we can pull out certain things that are important to composers, like the speed and ease of creating and exploring mappings, access to surprise and discovery, and balancing surprise and complexity with predictability and control. And here I'm really talking about expressive instrument building, not the sort of things that we're doing with the cabo. But here, again, interactive machine learning ends up being really useful as a tool for each of these things. And comparing what people have written about in the larger human-computer interaction literature about what makes a good creativity support tool. These are the sorts of things that they write about in architecture, in engineering, in writing. And supervised learning ends up just meeting a lot of these criteria in very nice ways. So this is definitely an application for future work for us. So I'm going to wrap up the talk here. I'll skip this because I talked about it already. I think this is really useful stuff because it's a good fit for the problems that we're interested in, and it's also usable by people without programming or machine learning expertise. There are a lot of... yeah, so my current work, and I can talk about this afterwards if you want, I'm talking to rehabilitation therapists, people working with kids with cerebral palsy. They're building gestural control systems that are customized to users, that allow people to be creative and expressive when they're doing their exercises that they have to do 100 times a day that are really painful. So that's the next kind of round of non-musical work that I'm looking at. All right, so my last 2 points that I want to leave with before people want to eat lunch or ask me questions. Number one, musicians are awesome collaborators. They're really fun to work with. They're highly motivated and adventurous. So I think this work has been allowed us to learn a lot about interactive machine learning that has implications beyond music, but we've learned it because we're working with users who actually care and actually use it in their everyday work. And then finally, in terms of my own larger research, I think that applied machine learning should be studied further as a human-computer interaction domain. And that's really what I'm doing right now in my postdoc. So thank you so much for coming. Thanks, on behalf of Meg, too, and to all these people who supported this work. So.
One thing to note, too, before you leave, tonight, 7:30, over in the Music and Dramatic Arts building, the Studio Theater over there, is a concert using